This is a presentation on internal energy and its relationship to enthalpy. So let's look at changes in internal energy, or delta E. The internal energy, or E, is all of the energy contained within a substance or a particular system. The function includes all forms of energy such as kinetic, potential, gravitational, electromagnetic, so on and so forth. So the change in internal energy would be equal to the internal energy of the products minus the internal energy of the reactants. So E is equal to Q plus W. So if Q is greater than 0, the heat is absorbed by the system. If Q is less than 0, if delta E is negative, then energy is released by the system undergoing a chemical or physical change. The energy can be written as a product of the process. Delta E is positive when energy is absorbed by a system undergoing a chemical or physical change. Energy can be written as a reaction. So let's look at this example. If 1200 joules of heat are added to the system at energy state E1, and the system does 800 joules of work on the surroundings, what is the energy change of the system, or delta E of the system? So let's talk about work in terms of pressure volume. In most chemical or physical changes, the only kind of work would be pressure volume work. Pressure is defined as force per unit area. Usually only perform useful work if it's contained within, say, a piston or something. Using the ideal gas equation, PV equals nRT, which if you look at your gas laws, that is the ideal gas law equation. We can look at volume changes of ideal gases at constant temperature and pressure due to changes in number of moles of gas, and relate the work So how could a gas do work? Say if we put it in a piston here, and say I've got some dry ice in the bottom of that piston, and I allow it to sublime over time. So when I do that, notice the piston is pushed up as the dry ice disappears and goes. So our work is equal to force times distance, which is equal to a negative PV, so that we get our signage right, which is equal to negative delta N RT. In the previous case, it would be more convenient to look at the change in the moles of gas, potentially if I've got a written reaction. Consequently, there are three possibilities for volume changes, depending on the type of reaction. There are some cases where they're equal, as in case 1, so P delta V equals 0, the change in moles of gas equals 0, which means no pressure volume work. If you look at carbon monoxide, so let's consider the following gas phase reaction at constant temperature and pressure and determine whether work is done on the system, on the surroundings, or whether no work is done at all. If we look at A, I've got 2 moles of nitrogen monoxide plus 1 mole of oxygen gas going to form 2 moles of So let's look at the relationship of delta H to delta E, because we use delta H a lot more in chemistry. The total amount of heat energy that a system can provide to its surroundings at a constant temperature and pressure would be given by delta H is equal to delta E plus P delta V. Now, in many cases, a reaction that's open to the atmosphere in the room, the volume change is very small or equal to 0. So if delta V is approximately 0, then P delta V is approximately 0. And so delta H is approximately equal to delta E because that P delta V term drops out. This is why in most ordinary chemical reactions just open to the room and not in a piston or anything, we'll use delta H instead of delta E. The change in enthalpy, or delta H, which is called the heat of the reaction, is the amount of heat absorbed or released when a reaction occurs at constant pressure. So let's look at one last example. Look at the relationship between delta H and delta E. So enthalpy of the combustion of pentane C5H12 is a negative 3523 kilojoules per mole under standard conditions. The combustion of 1 mole of N-pentane at constant pressure, therefore,